Just 25 light years from where you're sitting right now, astronomers have found a planet that receives almost exactly the same amount of sunlight as Earth does, sits inside its star's habitable zone, and might even have the right kind of atmosphere to support liquid water on its surface. This isn't a distant speculative maybe. This is a real peer-reviewed discovery in the summer of 2026, and it's already being called one of the most Earth-like planets ever found. In this video, we're going to break down exactly what scientists discovered, how they found it, what makes it so genuinely exciting rather than just another exaggerated headline, and what still has to happen before anyone can say with confidence whether this world could actually support life. If you enjoy real, grounded space science instead of speculation dressed up as fact, stick around till the end. It's worth acknowledging up front that the phrase "most Earth-like planet ever discovered" has been used many times before about many different planets over the past 2 decades. Names like Kepler 452b, Proxima Centauri b, and the TRAPPIST-1 system have all carried that same headline at various points. So the natural question is, what makes this particular claim about this particular planet worth taking seriously rather than dismissing as just another recycled headline? The answer lies in exactly how closely this planet's specific numbers line up with Earth's, and in understanding precisely what still remains unknown. Let's start with the basics. The planet in question is called GJ 338b, and it was discovered by a team led by astronomers at the University of California, Irvine, with the findings published in the Astrophysical Journal. The research was led by Paul Robertson, an associate professor of astronomy at UC Irvine, and it involved collaborators from the University of Texas at Austin, Penn State University, and other institutions. The planet orbits a star roughly 25 light-years away from our solar system, which sounds like an enormous distance by any everyday human standard, but in astronomical terms, it's essentially right next door. Robertson himself put this into perspective in a way that's worth repeating because it really does reframe how close this discovery actually is. The Milky Way galaxy is about 100,000 light-years across from end to end. A planet 25 light-years away is, relatively speaking, one of our closest cosmic neighbors, practically in our own backyard when you consider the true scale of the galaxy we live in. That proximity matters enormously for future research because the closer a planet is to us, the more detail future telescopes will eventually be able to observe about it. GJ 3378b orbits a red dwarf star, which is a smaller, cooler, dimmer type of star compared to our Sun. Red dwarfs are actually the most common type of star in the entire galaxy, making up a large majority of all stars that exist, and in recent years, they've become a major focus for scientists hunting for potentially habitable worlds. Because red dwarfs are cooler and fainter than Sun-like stars, their habitable zones, the region around a star where temperatures could allow liquid water to exist on a planet's surface, sit much closer to the star itself than our own solar system's habitable zone does. This particular planet is roughly twice the size of Earth, making it what astronomers call a super-Earth, a category of planet larger than our own, but still considered rocky, rather than a gas giant like Jupiter or Neptune. Its minimum mass works out to just over twice that of Earth as well, which is an important detail because a planet's mass tells scientists a lot about whether it's likely to be a solid rocky world capable of holding onto an atmosphere rather than a puffy, gas-dominated planet with no real surface at all. Here's the detail that's generating the most excitement, and it's worth sitting with for a moment. GJ 3378b receives about 90% of the radiation from its host star that Earth receives from the Sun. Robertson described this as being right in the sweet spot. To put that in context, most exoplanets that get labeled Earth-like in headlines are wildly different from Earth in terms of the actual energy they receive from their star. Some are scorched, tidally locked worlds where one side permanently faces blazing heat while the other freezes in eternal darkness, and others sit at the very edge of the habitable zone, barely warm enough to avoid being frozen solid. GJ 3378b, by comparison, is getting almost exactly the kind of stellar energy budget that Earth gets, which is a genuinely rare and significant find. It's worth taking a moment to compare GJ 3378b to some of the previous planets that have carried the Earth-like label, because the differences actually matter quite a lot. Kepler 452b, discovered years ago by NASA's Kepler Space Telescope, orbits a Sun-like star and is often called Earth's cousin, but it's about 60% larger than Earth and sits roughly 1 to 400 light-years away, far too distant for any near-term follow-up observation with current or even near-future telescopes. Proxima Centauri b, orbiting the closest star to our Sun, is exciting because of its extreme proximity, just over 4 light-years away, but it orbits a small, highly active red dwarf star that produces powerful flares, raising serious questions about whether any atmosphere could survive there long-term. The TRAPPIST-1 system, with its 7 roughly Earth-sized planets, generated enormous excitement, but several of its planets are likely tidally locked, meaning one side permanently faces the star while the other remains in permanent darkness, creating extreme conditions unlike anything on Earth. GJ 3378b doesn't automatically solve every one of these issues either, but it does combine several favorable factors that don't always line up together in a single planet. A distance close enough for meaningful future study, a stellar radiation level nearly identical to Earth's own, and a size and mass consistent with a genuinely rocky, potentially atmosphere-retaining world. That combination, rather than any single spectacular feature, is what makes astronomers describe this discovery as particularly promising, rather than simply another entry on an already long list. The Habitable Zone Planet Finder, mounted on the Hobby-Eberly Telescope at McDonald Observatory in Texas, and the NEID spectrometer on the WIYN telescope at Kitt Peak National Observatory in Arizona. Both of these instruments use what's called the radial velocity method to detect planets. Rather than directly seeing the planet itself, which is essentially impossible given the enormous distances and the overwhelming brightness of stars compared to planets, these instruments detect the tiny gravitational wobble a planet induces in its host star as it orbits. As the planet's gravity tugs the star slightly back and forth, the star's light shifts in very precise, measurable ways, and from that wobble, astronomers can calculate the planet's mass, its orbital period, and its distance from the star. This is a remarkably indirect way of seeing a planet, and it's a good reminder of just how much modern astronomy depends on painstakingly precise measurements rather than simple visual observation. The wobble a planet like GJ 3378b induces in its star is incredibly tiny. We're talking about detecting stellar motion on the order of a few meters per second, roughly walking pace, across a distance of 25 light-years. The fact that instruments can measure something this subtle from this far away is itself an extraordinary feat of engineering and scientific precision. To put this in perspective, imagine trying to detect someone gently swaying back and forth while standing on a stage from a distance so great that even light takes 25 years to travel there. That's roughly the scale of precision astronomers are working with when they use the radial velocity method. The Habitable Zone Planet Finder and the NEID spectrometer are both specifically engineered instruments built to detect these minuscule shifts in a star's light spectrum, called Doppler shifts, which occur as the star moves very slightly toward and away from Earth in response to the planet's gravity. Confirming a planet this way typically requires observing the same star repeatedly over months or years, gathering enough data points to be statistically confident that the pattern being observed is a genuine planetary signal and not simply noise stellar activity, or some other confounding factor. This is where the concept of the cosmic shoreline becomes central to the whole story. The cosmic shoreline is a term astronomers use to describe a rough boundary around a star based on how much radiation a planet receives that determines whether that planet is likely to retain an atmosphere or have it stripped away entirely by stellar radiation. Planets that sit safely on one side of this boundary tend to hold onto thick protective atmospheres. Planets on the other side tend to end up essentially airless, their original atmospheres blasted away by the star's radiation and stellar wind over billions of years. The idea behind the cosmic shoreline comes from comparing planets across our own solar system and plotting them by two factors: how much stellar radiation they receive and their escape velocity, which is essentially a measure of how strongly a planet's gravity holds onto its atmosphere. When astronomers plot every planet and moon in our solar system this way, a surprisingly clean pattern emerges, a rough dividing line where, on one side, worlds like Earth and Venus have managed to retain substantial atmospheres, while on the other side, worlds like Mercury and our own moon have ended up essentially airless. This pattern gives scientists a rough predictive tool they can apply to planets outside our solar system too, even without being able to directly observe their atmospheres yet. GJ 3378b sits almost exactly on this cosmic shoreline boundary, which makes it an extraordinarily interesting test case. It's not safely tucked well inside the atmosphere retaining zone the way Earth is, and it's not obviously doomed to be airless either. It's sitting right at the edge in a zone where the outcome could genuinely go either way, and that ambiguity is exactly what makes this discovery scientifically valuable rather than just another entry on a long list of potentially habitable exoplanets. Our own solar system actually gives us a perfect real-world example of how this cosmic shoreline concept plays out in practice, and it's a planet we know incredibly well: Mars. Scientists believe Mars once had a much thicker atmosphere and quite possibly liquid water flowing across its surface billions of years ago. But because Mars lacks a strong global magnetic field to shield it, and because it receives significant solar radiation without adequate protection, its atmosphere was gradually stripped away over time, leaving behind the thin, cold, mostly airless world we see today. Mars is essentially a real-world cautionary tale about what happens to a planet that ends up on the wrong side of the cosmic shoreline. Robertson used a particularly vivid analogy to describe just how thin a planet's atmosphere actually needs to be to support life. And it's worth repeating because it really puts things in perspective. He explained that if you scaled Earth down to the size of an apple, our entire atmosphere would only be about as thick as the apple's skin. That thin, fragile layer is what maintains the surface pressure necessary for liquid water to exist, provides breathable air, and offers some meaningful protection from the harsh radiation environment of space. It's a genuinely humbling thought. The difference between a living world and a dead one can come down to something as proportionally thin as the skin on a piece of fruit. This analogy also helps explain why detecting an atmosphere from 25 light-years away is such a monumental technical challenge. Scientists aren't just trying to spot a planet, they're trying to detect a layer of gas so thin relative to the planet itself that it's genuinely comparable to detecting the skin of an apple from an almost unimaginable distance, using nothing but the faint starlight that happens to pass through or reflect off that razor-thin layer during a transit or through direct imaging. It's precisely this kind of extreme technical demand that current telescopes simply aren't built to meet, and why a purpose-built instrument like the Habitable Worlds Observatory is considered necessary rather than optional for this next phase of research. This is exactly why scientists are being cautious rather than making sweeping declarations about GJ 3378b's habitability. Right now, nobody actually knows whether this planet has retained any kind of meaningful atmosphere. It's entirely possible that GJ 3378b, despite sitting in the habitable zone and receiving nearly Earth-identical amounts of starlight, could be a barren, atmosphere-stripped rock, not unlike a slightly larger version of Mars. It's equally possible that it has managed to hold onto a protective atmosphere, in which case it becomes one of the most compelling candidates for a genuinely habitable world that we've ever identified. A member of Robertson's research team, UC Irvine student Gogod James, worked specifically on characterizing the size of GJ 3378b and emphasized that if this planet does turn out to have a proper atmosphere, it would justify serious further research into biosignatures, meaning chemical signs in the planet's atmosphere that could indicate biological activity, as well as searches for liquid water and other indicators of a genuinely life-supporting environment. But all of that depends entirely on confirming whether an atmosphere is actually there in the first place. And with current technology, that confirmation simply isn't possible yet. This brings us to an important, if slightly disappointing, reality check. We're not going to get a definitive answer about GJ 3378b's atmosphere anytime particularly soon. The instrument capable of actually resolving this question is NASA's planned Habitable Worlds Observatory, a next-generation space telescope specifically designed to directly image exoplanets like this one and analyze their atmospheres in detail. The problem is that this observatory isn't expected to launch until sometime in the 2040s. That means it could be well over a decade before scientists have the technological capability to actually confirm whether GJ 3378b has an atmosphere, let alone whether that atmosphere contains anything resembling a biosignature. This timeline is worth sitting with for a moment because it says something important about how real scientific discovery actually works, as opposed to how it's often portrayed in sensationalized media coverage. Finding a planet like GJ 3378b isn't the finish line. It's closer to the starting line of a much longer investigation. The discovery itself, confirming the planet's existence, its size, its mass, its orbital distance, and its position relative to the habitable zone, is already a significant scientific achievement. But answering the ultimate question everyone actually wants answered, could life exist there, requires technology that, in some cases, hasn't even been built yet. It's also worth putting this discovery into the broader context of exoplanet science as a whole. Since the first confirmed exoplanet was discovered back in 1992, orbiting a distant pulsar more than 2,300 light-years from Earth, astronomers have gone on to confirm more than 6,000 exoplanets scattered across the galaxy using a combination of ground-based and space-based telescopes. That number keeps climbing every year, and it has led researchers to a fairly remarkable conclusion. Nearly every star in the galaxy likely hosts at least one planet. The sheer diversity among these confirmed planets is staggering. Some are enormous gas giants larger than Jupiter, some are small and rocky like Earth and Mars, some orbit their stars in scorching, day-long orbits, and others drift through the emptiness of interstellar space entirely unattached to any star at all. Within that enormous and diverse catalog, though, planets like GJ 3378b remain relatively rare, because finding a world that checks multiple key boxes simultaneously, roughly Earth-scale size, rocky composition, correct habitable zone positioning, and a stellar radiation environment genuinely comparable to Earth's, is still a significant challenge. Many previously announced Earth-like exoplanets fall short on one or more of these criteria once studied in greater detail. Some are the right size but orbit far too close or far too far from their star. Others sit in the habitable zone but around stars so different from the Sun that the actual conditions on the planet's surface would be nothing like Earth's. GJ 3378b stands out specifically because it manages to satisfy several of these criteria at once, which is part of why Robertson and his team described this particular discovery as exciting. There's also something worth appreciating about the sheer methodical, patient nature of the science behind this discovery. This wasn't a chance observation or a lucky break. It was the product of years of precise, repeated measurements using two separate, highly sensitive instruments on two different telescopes, cross-checking each other's data to build enough confidence in the result to publish it in a peer-reviewed journal. Exoplanet hunting, especially using the radial velocity method, requires collecting data over long periods of time, since astronomers need to observe a star's subtle wobble across multiple orbital cycles of the planet to be confident they're seeing a real signal rather than noise or a false positive. It's also worth acknowledging that this discovery fits into a much larger, ongoing pattern in astronomy. The recognition that potentially Earth-like planets around red dwarf stars might be far more common throughout the galaxy than scientists once assumed. Because red dwarfs are so numerous, making up an estimated 70 to 80% of all stars in the Milky Way, and because their habitable zones sit close enough to the star that even ground-based telescopes using current technology can detect planets within them, red dwarf systems have become one of the most productive hunting grounds for exoplanet discoveries in recent years. If a meaningful fraction of these countless red dwarf systems turn out to host planets similar to GJ 3378b, it would suggest that potentially habitable worlds could be dramatically more common throughout the galaxy than earlier estimates suggested. That said, it's worth being upfront about some of the genuine challenges and open questions specific to red dwarf systems, because they complicate the picture in ways that are important to understand rather than gloss over. Red dwarf stars, despite being cooler and dimmer overall than the Sun, are often far more magnetically active, producing frequent and sometimes intense stellar flares. Because a planet in a red dwarf's habitable zone orbits so much closer to its star than Earth does to the Sun, it can be exposed to significantly more intense radiation during these flare events than Earth ever experiences from the Sun. This is part of why the question of atmospheric survival is so critical for planets like GJ 3378b. How an atmosphere isn't just important for maintaining surface conditions, it's also the planet's primary defense against this kind of stellar activity. There's an interesting silver lining to this challenge, though, which researchers have increasingly come to appreciate. A sufficiently thick and well-sustained atmosphere, combined with a planet's own magnetic field if it has one, can actually provide meaningful protection even against a fairly active red dwarf star. Earth's own atmosphere and magnetic field together shield us from a huge amount of solar radiation and charged particles that would otherwise be harmful. And there's no fundamental reason a rocky planet around a red dwarf couldn't develop similarly protective systems, assuming its atmosphere isn't stripped away before it has the chance to. This is precisely the kind of open question that makes GJ 3378b such a valuable case study. It sits in exactly the kind of environment where scientists need real data, not just theoretical modeling, to understand how these competing factors actually play out. Let's address a few common questions people tend to have about a discovery like this. Does this mean scientists have found signs of actual life on GJ 3378b? No. Nothing about this discovery indicates the presence of life. What's been confirmed is the planet's existence, its approximate size and mass, and its position within the habitable zone relative to its star, whether it has an atmosphere, and whether that atmosphere shows any signs consistent with biological activity remains completely unknown and won't be answered until significantly more advanced observational tools become available. Could humans ever travel to GJ 3378b? Not with any technology that exists today, or that's likely to exist within the next several generations. Even at 25 light-years away, which is considered close by galactic standards, traveling there using current propulsion technology would take tens of thousands of years. For context, even light itself, the fastest thing in the universe, takes 25 years just to make the one-way trip. Any serious discussion of GJ 3378b remains firmly in the realm of remote observation, not travel. Is there a chance this discovery could later be walked back or revised, the way some past exoplanet claims have been? It's possible, though the specific measurements involved here, the planet's mass, orbital period, and distance from its star, were obtained using two independent, well-established instruments and cross-checked against each other, which gives the core findings a fairly solid foundation. What remains genuinely uncertain isn't the planet's existence or its basic orbital characteristics, but rather the much harder question of its atmosphere and habitability, which nobody has claimed to have already answered. How does this discovery compare in significance to something like the James Webb Space Telescope's exoplanet observations? They're complementary rather than competing. Instruments like the Habitable Zone Planet Finder and NEID are excellent at detecting planets and precisely measuring their orbital characteristics through the radial velocity method, but they can't directly analyze a planet's atmosphere. Telescopes like James Webb and eventually the Habitable Worlds Observatory are built to do exactly that kind of atmospheric analysis, but they need a discovery like GJ3378b to already exist and be well characterized before they can decide it's worth pointing their limited observation time at. Why does it matter if we can't visit it or even confirm its habitability for years, maybe decades? Because every confirmed discovery like this adds another data point to one of humanity's oldest and most fundamental scientific questions. Are we alone in the universe? Each new Earth-sized planet found within a habitable zone, especially one receiving stellar radiation this close to what Earth receives, incrementally strengthens the case that potentially habitable environments might not be rare cosmic accidents, but a natural and fairly common outcome of how planetary systems form throughout the galaxy. It's also worth noting how this discovery reflects a broader shift happening in exoplanet science right now. A shift away from simply counting how many planets exist and toward carefully characterizing the handful of genuinely promising candidates in as much detail as current instruments allow. Early exoplanet surveys were largely about discovery for its own sake, cataloging thousands of worlds without much ability to study any individual planet in depth. Missions and instruments today, and the ones planned for the coming decades, are increasingly designed to take that next step, not just finding planets, but actually characterizing their atmospheres, their compositions, and ultimately, whether they show any signs of harboring life. GJ3378b sits precisely at this transition point, discovered and confirmed today, but genuinely understood only years from now. So, to bring this back to where we started, what did scientists actually find? A rocky, super-Earth-sized planet, roughly twice Earth's mass, orbiting a red dwarf star just 25 light-years away, sitting almost exactly in the habitable zone, and receiving nearly the same amount of stellar radiation that Earth receives from the Sun. It's one of the most compelling Earth-like planet candidates discovered to date, not because scientists have confirmed it's habitable, but because it checks so many of the right boxes simultaneously that it becomes an obvious priority target for the next generation of telescopes specifically built to answer the one question this discovery can't yet answer on its own. Does it actually have an atmosphere? And if so, what's inside it? Until NASA's Habitable Worlds Observatory or a similarly advanced instrument gets the chance to study GJ3378b directly, this remains an open, genuinely thrilling mystery rather than a confirmed habitable world. But that's exactly what makes it worth paying attention to. Somewhere out there, 25 light-years away, orbiting a faint red star, there's a planet that might be getting almost exactly the same warmth from its sun that we get from ours. And we simply don't know yet whether anything like life has ever had the chance to take hold there. Perhaps the most honest way to end this story is to acknowledge that we're living through the early, patient stages of a much longer scientific process. Every generation of astronomers builds the tools that the next generation will use to answer the questions the current generation can only ask. Robertson and his team have handed the next generation of scientists and the next generation of telescopes a genuinely promising target to point at. Whether GJ 3378b turns out to be a thriving life-bearing world, a barren rock like Mars, or something entirely in between, we won't know for years. But for now, having a real, nearby, carefully measured candidate this close to Earth's own conditions is itself a meaningful step forward. If you found this breakdown interesting, make sure to like this video, subscribe to the channel, and let us know in the comments. Do you think GJ 3378b will turn out to have a real atmosphere? Or will it end up being another Mars-like world that lost its air to its star long ago? See you in the next video with another real grounded space discovery worth exploring.